My name is Felipe, if you haven't met. I work with this in server engineering performance team with focus on storage mostly. Bootstorm as well, sometimes. And last year, or in October, I came here, Edinburgh, and talked to people about scaling performance on a single virtual disk basis. So what happened, and in which cases did we see more overhead when virtualizing on a single VM, single disk basis. So today I'm going to talk about something else. Since then, a lot has happened, and we've been focusing more and more on aggregate workloads and use cases. So I want to start about just drawing the lines on what exactly we're measuring now, and drawing attention to some of the dimensions out there when it comes to storage performance, and then talk a bit about the state of the art. I know a lot of people already know this, but there's I wanted to focus on the trade-offs between grand mapping, persistent grants, and grand copy, which is what we are using on Sun Server now. We're going to be using our next release, and then present some aggregate results on very, very fast local storage. So on the abstract of this talk, I said I was going to be doing over 7 gigabytes a second in a single host. That's out of date now. We're actually doing over 10. So we went double digits. It was pretty good. And talk about where we should go next after this. So in terms of dimensions of storage performance, you might have seen this slide. You have certainly seen this happening before. Someone gets some fast storage, and they run something like HDPalm or DD in a bare metal environment. And then they take this benchmark to the VM and measure again and assess what kind of overhead they're having and draw some conclusions from there. And this is not showing the full picture. So to be honest, it is a perfectly valid benchmark, and people still do this. I would probably do that. It just gives you a quick feel of what's going on. But what I much prefer doing is drawing a chart like that and having throughput on the y-axis and block size on the x-axis. So it will vary from a sector up to 4 megabytes and powers of 2, so that will be in logarithm scale. And I find normally that the curve looks like this. It gets faster and faster with larger block sizes, and eventually reach some sort of maximum, which sometimes is reaching the maximum that your storage can offer, sometimes it's some other type of bottleneck. So this gives you a better idea of what's going on, but it still doesn't, it's still not telling the full picture. When it comes to storage performance, there are many other dimensions you can look at. Some of them are more obvious, like I/O depth, or the number of threads you're using, or whether you're using read ahead, if it's reads or write, sequential random. There are other things that are less obvious. For example, the CP state configuration of your cores affects your performance a lot. The temperature in your server. There's a paper by the University of Toronto, I think, that's called "Some Might Like It Hot," and they show how commodity disks will perform much better at higher temperatures until they break. Well, SAS disks and other enterprise-grade disks will just slow themselves down when they start to get hot. Noise levels. There's a video on YouTube. I saw a guy showing some latency benchmark, and he goes in front of his server and screams, and the latency starts to get high. So depending where your servers are in your rack, maybe you're being affected by that too. So let me put some numbers and show what I mean there. So this is the scale I showed before. So throughput in megabytes a second versus block size, and how it gets faster. This is a single SSD. It's a Micron disk. And these measurements are made from DOM0. It's the simpler of possible cases. I kept I/O depth to one single thread, doing sequential reads and buffered. It doesn't quite look like that curve I showed before because we're not maxing out really anything. It looks like it could go faster, right? So what I did was basically just try to put more threads. What I'm talking about is aggregate workloads, right? So when I put more threads, up to 10 threads, then I see that line showing up on the top suggests I'm hitting some sort of limit there. And I can have a better idea of how this disk or how this kind of storage would behave with more threads. So I said it's kind of sequential because what I did was to partition this disk into 10 logical volumes, and I have a thread on each one of those logical volumes doing sequential I/O. So this looks like what VMs would be doing if I had this as my storage and would have 10 VMs on top of it. So how does that compare to 10 VMs doing I/O in here? So again, if this was the single thread and I compare that to a single VM, I know it's really, really hard. Can you see that green there? Weird. it looks like it's lower, it's not maxing out, because the latency is higher from the virtual machine, and this disk operates at a very, very low latency. So what I'm interested in knowing is if I had 10 VMs, if it would match what I saw before with the 10 threads in DOM0. So this is the line for the 10 threads, and this is the line for 10 VMs. It looks a bit strange there. It's not wrong. It's just that I'm not using indirect I/O in TAP-DIS3. So when I have larger blocks, those requests are being broken up, and I'm actually getting a bigger I/O death here unintentionally. It has that effect. So you see that 10 VMs didn't really match for those smaller block sizes, a little bit slower, but I eventually reached the maximum of this disk. What I want to know next is what's going to happen when I have more and more disks here. So the actual measurements I made were with more of these SSDs and all the types of SSDs together. I'll get to that. Before I go there, I wanted to just briefly discuss the pros and cons of each one of these grand mapping, persistent grants kind of stuff. So most people should know how grand mapping normally works. Block front will get some requests with pages associated in the guest memory space. The backend will map that, having some page grants, and this is what's going to be associated with the requests that eventually leave your host. So the pros of this is that there are no copies involved. When done in the kernel, it's a really low latency alternative. So there are still room for improvement. And when I say when done in the kernel, it's because you could have QEMU or something else doing the maps through the grand device in user space, and that, of course, will add a lot of latency. And the cons are listed, it's not network safe. So what I mean by not network safe is that there are still some issues, apparently, when the backend over there is an iSCSI LUN or an NFS share. And if you have requests in flight and the domain is destroyed, or if you have retransmission, TCP packets queued for retransmission, and the NFS RPC actually completes while those packets are scheduled, you might unmap those grants and then find that you need to retransmit data that you no longer have. And we're not completely convinced that this is safe. The other con on the list is that this is a bit hard on the grant table, so we're still seeing some, there were improvements since we last talked in October, but we are still seeing some problems with the scalability here. I'm not entirely sure why yet. Looking forward to seeing perf fixed and finding out more about this. So persistent grants is slightly different. What's persistent grants is block front and block back are going to try to keep some of those maps established, and the block front will bounce data in and out from this persistently mapped grants. So David mentioned this morning that one of the improvements we had recently was when the front end knows that the back end is not doing persistent grants, then it will not copy. When this was first implemented, the block front would always bounce stuff around, which added a lot to the latency. So it is easier on the grant tables. And I listed copies on the front end being a pro, but at the same time, copies involved being something bad. We prefer not to copy, of course, but if you copy, at least this is happening on the front end, which is a good thing for purpose of caching and other, and doing work in the guest vCPUs and not DOM0. So there's a third thing here, actually, before I talk about grant copy, which is what we've been doing in Zen Server until now, which is the TAP-DIS2, block TAP2, block back approach. So basically, in Zen Server, we wanted to have we wanted to make sure we were safe when we operate on top of network backends, and we wanted to support the VHD format for theme provision, cloning, snapshotting, etc. And we did this through a little daemon in user space there in DOM0, which is called TAP-DIS2. And to interface TAP-DIS2 block back, we implemented block TAP2, which is just a fake block device in DOM0 that block back can talk to. So at that point, those requests are associated with the page grants as well. But block TAP2 will copy that data to a set of local pages, and then TAP-DIS2 will eventually issue those requests back using local pages, so the requests are associated with data that is local to DOM0, not foreign. So on the pro side, we have now it is now safe, and it has all these neat features because we use VHD. On the con side, there's copies involved. It's still hard in the grant tables. You use a lot more memory than you should. And it's really not scaling when we have this kind of newer storage. So a few years ago, this was fine, and now we need to do something different. So we did grant copy. So what we do grant copy is basically we upgraded the version number on TAP-DIS3, and we have TAP-DIS3 allocating pages and requesting the grant device to do a copy instead of doing a full map of this. So Zen actually copies the data that's been granted around without a map and map overhead. So we have the local pages. It's easy on the grant tables. By having local pages now, we're safe. The copies are on the back end, which is a bit bad because we end up needing a lot of DOM0 vCPU power to scale properly. So I have a little table comparing all of this for the sake of seeing everything on the same slide, I guess. And the grant mapping looks like it should be the best thing we have. We just should perhaps work further on that. So let me show you some results and how do we get to the 10 GB a second mark. So my test environment was the fastest thing I could get my hands on at the time. It was an R720 Intel server with 24 threads, so 2 sockets, 6 core sockets with hyper-threading, a 3.5 GHz plus turbo. So unless I marked differently, I gave 24 vCPUs to DOM0 for the grant copy to scale properly, but I did measure different configurations where I thought it was appropriate. And the storage side, which is the interesting bit, I used 4 of those Micron SSDs I showed in the beginning of the presentation. Another 2 Intel P3700, so this is the newest Intel Enterprise class SSDs, PCIe, NVMe, etc. And a Fusion IO drive we happen to have hanging around that I put in there as well. I had to be a bit careful with how I put these disks in the machine, but one, because they wouldn't fit. It's just a lot of PCIe cards. And secondly, because it was very easy to actually max out the PCIe lanes to that particular core, so I had to put a particular socket. So I had to arrange I arranged the 4 microns in one, mapped to one socket, and the other 3 SSDs to the other. And this is how I mapped them to the VMs. So for each SSD, I created 10 logical volumes inside, and for each VM, I had up to 10 VMs. For each VM, I associated logical volume of each SSD to a guest. So each one of my guests had 7 virtual disks. I'm not interested in the performance I'm getting out of individual SSDs. So I only consider the total amount of data that was transferred by one guest over those 7 virtual disks over a period of time. So for baselining, I first measured what this workload would look like from DOM0. So I first had 7 threads in DOM0 reading from 1 logical volume on each one of these disks, and then I increased to 14 threads, etc. And it looked more or less like this. So we went up to about 13 GB a second doing sequential reads. There is a little bit of a dodgy line there on the bottom, if you notice. What's happening there is just that some of those disks were responding quite fast, probably faster than they should. The drivers were a bit experimental for requests up to 128K. So if you want to visualize that, the red line should just be going below the green for that particular range. Everything else makes perfect sense. And I kept that in mind as a baseline curve, and then started to measure from guests. So I intentionally started with the worst possible case. I picked QEMU disk, compiled it for this version of Zen server, and removed persistent grants. So it does grant mapping via the grant device. It looks like this. It's pretty bad. But we don't expect anyone to be using that. It's just for the sake of comparing it. And then I re-enabled persistent grants and I measured it again. So it looks a lot better. It goes up to about 6 GB a second at some point. It appears to me that the bottleneck there was we only have 1 QEMU process per guest, and I have 7 virtual disks there. And that process is rotating to all of those rings, issuing POSIX IO reads down to the device. And it just looked like, even though they were cloning themselves to do the actual operation, there was some overhead involved. I didn't really dig much into that. I did find a node discussion in the list. I think it was Stefan and Ian Jackson talked about having a single QEMU, whether or not that was a problem. Maybe now we have storage to test that again and see how it could be done different. The other thing I measured, which was also known to be bad, was the tap disk block tap 2 design that we have in the server today in Clearwater. And this doesn't have anything like persistent grants or indirect I/O. It uses the block back from the 310 kernel, but with block tap 2 and tap disk 2, it doesn't scale very well. There are some dodgy problems down there. What I tried to do is just replace block back with a newer one, which has persistent grants and indirect I/O, and it got a lot better. which was surprising actually, going through box type 2 and type 2 that would scale this much. So the single thread case is pretty bad, but the others went up to about 7. I didn't have time to debug this in detail. I just looked at there was apparently some contention around some PV spin locks. So we're using PV spin locks on 310. Maybe we should try ticket locks or something else. I also tried, because there was some indication of lock problems, to just reduce the count of DOM0 VCPUs from 24 down to 8, and increase the number of VCPUs to the guests from 2 to 6. So after all, block front's now doing copies in the front end, and it got to be better. Actually touched the 10 kilobyte a second mark. So this is the same design, but actually, sorry, this one is not using the block type 2 data path. It's just the block back directly to the logical volume. So it got pretty fast there. But what was fastest of all was actually TAP3 doing grand copy, and it looked like that. So it was consistent, just above 10 gigabytes a second with 3 guests or more. And the bottleneck apparently was the VCP utilizations, and just had all TAP just copying a lot of stuff all the time. And that's the reason I believe it didn't actually go faster and match the actual power that I saw from DOM0. So what do I think we should look into next is, well, there's still problems with the single VBD scalability, right? So what the little diagram I made there is basically that before we had the time to do all those operations between the guest and DOM0 to be in orders of microseconds, and disks were responding in the order of milliseconds. And now when they respond in the same order, then everything we do in the host counts, copying and mapping, doing expensive operations. And that's what explains this difference here. My question is, what happened when these disks actually start to get even faster and respond to very intensive I/O deaths? So if we don't start looking into that now, we might find that when we actually put those disks and start using, we're not going to be performing very well. The other problem that I see is the fact that the I/O death will be limited to 32 when we're using a single page for the ring. So I think people can say two things here. One is, yeah, but is it realistic that people are going to be trying to do more than 32 outstanding requests on a single VBD? And even if so, we have multi-page rings, right? Well, kind of, yes, but if we look at that Micron SSD I had, which I know can deliver about 400,000 IOPS with 4K requests doing simple reads. So if I put the guest away for a second and just run FIO there with one thread and vary my IO depth, I'll find that FIO is using libIO, so it's doing IO submit and then IO get events. So that's the CPU work we'll be doing. And with one thread, with one outstanding request at a time, and 4K requests, I measured that it does about 15,000 IOPS and uses about 15% CPU time. As I increase IO depth, it goes up to 190,000 IOPS. And at that point, on this particular server, it was using 100% of a CPU. So here you see how the actual configuration of your processors affect your storage performance a lot. And if I increase the IO depth further, things really didn't change much. It probably queued things slightly better, did at 195,000 IOPS, but it was still maxed out because it was a single thread spending the whole time doing IO submit and IO get events. I actually found that to achieve those 515,000 IOPS, I had to use 5 threads in FIO. So if you go back to the guest case and we imagine we're using blockback, what happens is if you run FIO inside the guest and you go up to that same configuration I had before, one thread inside the guest and 32 outstanding requests, I measured that Xentop was reporting that DOM0 was using 120% of CPU time. So probably blockback was at 100% plus some other operations going on there. If I increase the number of threads, I couldn't see much improvement in the ops as well because the backend is bottlenecked there. So we should probably look into finding ways of having more threads handling a single disk. This is not very realistic anymore. I've seen people measuring SQL benchmarks inside guests and doing this kind of tests. So this is something that has nothing to do with the fact that that this first case would be slower, but this should scale ideally, and then we could make it scale. So this is an area for improvement. So for the multiple VBD case, I think that persistent grants and grant copy are offering interesting alternatives today. TAP3 with what it's doing, it's scaling well by going around locking things in the grant table. It is a excuse me, it is a network-friendly alternative. QDisk, on the other hand, has the copies on the front end. So by QDisk, I mean the persistent grant implementation could be blocked back as well. But both of them are adding extra copies, right? So ideally, we should be avoiding extra copies. And we should try to make this grant operation scale better. So there are some ideas floating around that. And we should try to get these network retransmission issues addressed properly if they still are really there, or prove that they aren't. There are many ideas here for improvements. We've tested that we could, for example, when we get some requests from the front end, we could switch the event channel mechanism. Instead of waiting for kicks, we could go into polling for a little while. So we have some measurements on that. They gave promising results. It was just a prototype at the time. There are some other ideas of I think how we can change, and I think this is the time to start doing that. So that's why there's a BOF session proposed for 5 o'clock, I think, where we could talk on how to adjust this design of systems to work with those new NVMe drives. So some ideas would be, for example, to plug block back directly to the driver and bypass the block layer entirely in DOM0, finding ways of doing thin provisioning, snapshotting, etc. on kernel-only data paths. And that's pretty much it. I tried to finish on time. I think there's still 5 minutes left. I have some support slides on interesting things, like what happens when the fans were not set for full speed. So I can take some questions if you have any. Yes? Hello?
So you mentioned some of the grant operations have been in circulation. Are you referring to patches that Amazon posted?
Yes, the Steve Wilson's patches.
All right.
We measured them. We struggled a bit to see some of the improvements, but there were some. There's just, it didn't fix all the problems we're seeing.
Okay. The other thing that you didn't mention, which I'm curious what you mentioned, is multi-queue.
Oh yeah, so this is something we're actually starting to talk about as well. How should we adapt the new multi-queue block layer to what we're doing in Zen? I don't have an answer for that yet. We're just starting to think about it. Oh, okay, apparently there are answers in the audience. Good. I'm sure you come at 5 o'clock and talk to us on a VOF session. Cool. So yeah, this is something we should start looking into. Every time I talk to David about it, he says, I'm waiting for you to implement it.
When you did all those vCPUs in your benchmarks, were you pinning those vCPUs?
At first I was, and then when I wanted to use 24 vCPUs to DOM0, I decided not to pin, because the machine only had 24 CPUs, and I wanted to give Zen freedom to move them about if needed.
So only use 22
I tried that, 22 and 22 pinned. So we do something in Zen server which we call exclusive pinning, which basically is to pin all DOM0 vCPUs to specific cores, and then pin the remaining cores to all the guests, vCPUs. So we have some things in the two stack to do that. There are some considerations with that, but it works. For some workloads, it's very helpful. When you need to ensure that DOM0 will have time to run, we do that. But for this particular case, I actually measured that, and I found that this was the best configuration for this kind of workload. So these are things that I think people need to experiment with, depending on what they want to do. If they want lower latency, if they want to allow for better scalability. I don't know if there are many people there with this kind of hardware configuration actually, but this is pretty fast storage. So I found that some customers are using, for example, a fiber channel with flash arrays outside of the host. So they're slightly different than this. Hello.
So in the test you showed before, so you were using several VBDs, right? For each
Yes, seven.
Okay.
Yeah.
So on a single VBD, how would it look like, say, QDisk versus TAP3?
I wasn't trying to say that one was better than the other. I didn't really measure that specifically, but I can definitely do that and share results on the list later while I still have the machine up and running. So this is the QDisk that it compiles by default in Zen 4.4. I think it's not the upstream QEMU. I just took the one from our build system and they asked you to compile QEMU for me and used that one, which had QDISC embedded. There was an interesting thing when I did that, which was the usage of ODirect. So there's been a lot of discussion around whether or not to use ODirect. Actually, the first slides I have for support is QDISC ODirect on top of a single micron. So with ODirect, I found that for larger block sizes, this was happening. It's horrible. You see how fast it is for the lower block size if compared to when ODirect is used. So if you just flick between the two, without ODirect, it's a lot faster. But I think that I didn't really look at what was going on. I just measured and got the results. I think what's happening on the larger block size is that we're maybe copying in the front end and then copying again, bouncing buffers around. I haven't really looked, but this at first I was a bit worried like that this was going far too fast, and I was like, there's something wrong. And then I measured the whole spectrum of threads versus all the block sizes, and this graph came up. And realized, oh, maybe it's going faster because of ODirect. So I set direct IO safe on and measured again, and it looked like that. It's exactly the same environment. That was the only difference. This is a single VBD per VM. Yeah, it maxes out the single SSD at 1.7 gigabytes. Tap disk does the same. It maxes out. I haven't put them side by side. I think I haven't.
No, is blockback still better than this?
Blockback is much better than this, yeah. Interestingly, but that's a different scale now. That's all the disks on. This was an interesting one. This is tap disk 3 with the thermal control set to maximum performance. There's a hidden setting on the iDirect there. And this is when I changed it to automatic. So automatic thermal control. So that was happening. So that was, when I saw that first, I was like, what's going on there? Maybe a profile around. Then I think it was Malcolm pointed out, said, you might be pushing it a lot on your processors at that level. It's 10 gigabytes a second. So I think if you're overheating, your cores will be slowing themselves down and not reporting anything. So I found in the past that when I was overheating the Fusion IO, it actually reported on the console. The driver wrote, oh, I'm going to clock down because I'm too hot. But you don't normally see that anywhere, so it was hard to find that was going on. And this was the difference between having 8 or 24 vCPUs. So I think this is 8 vCPUs in DOM0, and that is 24 on blockback from 3.16, which is pretty much the same as I think 3.13 or the last changes went in, and plugging them directly to the guests.
Now, the guests you said, were they PV or PVHP?
They are PV guests, just normal 64-bit Ubuntu Trusty with, in this case, 6 vCPUs and half a gig of RAM. I think I'm up for time. Thank you very much. If you want to talk later, there's a BOF. If you have other questions, please see me. Thanks.